Hello. Last time we were talking about the central limit theorem, and we were talking about this correction factor, right? So if you think about it, right, um, remember that the mean of the sampling distribution equals, or eventually after you do sampling, the mean of the population equals the mean of the sampling distribution. This is one statement that we talked about in class before, and I show you why this is true. And then the standard deviation of the sampling distribution equals the standard deviation of the population divided by the square root of the sample, right? So just recall that this is the mean of the sampling distribution, right? And this is the standard deviation of the sampling distribution. Okay? Or standard error, right? So this is this, right? And you need to remember this stuff, right? So now we were talking about this concept, right? Finite population correction factor. Oh, just in case, what is sampling? Sampling means just if I have an unknown or known population, right? If I want to make an inference about the parameter, like let's say about the mean, right? If you want to make an inference, if you have an unknown parameter, you could take sample, like a sample, let's say x bar 1, x bar 2, x bar 3, and x bar 4, and the sum of this sampling distribution, it states that as long as the sample size are large enough, then your sampling distribution eventually will approximate, the mean of the sampling distribution will approximately the population mean, right? So that's the whole concept about the central limit theorem, right? The more samples you take, the better the approximation, right? Or the better the inference that you're making. So that's the whole point about sampling distribution, right? Regardless of the distribution, right? The distribution might be skewed, or it might be, it doesn't matter what shape it is, right? But the more samples you take, right, the more normal the distribution will approach, right? If your distribution is normal, then that means the sampling distribution is going to be normal. If the distribution is skewed, then you make sure that when you're taking your samples, or when you're doing the sampling distribution, the sample size, they should be n greater or equal than 30, right? So that's the whole concept. And now let's approach this idea, right? So here they said the finite population correction factor. So the formula for standard error of the mean is accurate when the samples are drawn with replacement or are drawn without replacement from a large or infinite population, right? So they say a correction factor is necessary for computing the standard error of the mean for samples drawn without replacement from a finite population. So this is the most important part, this part right here, right? When the samples drawn without replacement from a finite population. So let's do an example so it makes sense to you. So here they're asking you, let me make it bigger. He said, in exercise 26 and 27, check to see whether the correction factor should be used. If so, be sure to include it in the calculations, right? So I have that problem here, right? Let me erase this stuff and we start from scratch. So here they're asking you, in a study of the life expectancy of 500 people, so in a certain geographic in the study of a study of the life expectancy of 500 people in a certain geographic region, the mean age at death was 72 years, and the standard deviation was 5.3. If the sample of 50 people from this region is selected, find the probability the mean life expectancy will be less than 70 years. So here you can see clearly that in the study of the life expectancy of 500 people in a certain geographic region, so they are already giving you here what? They're giving you the population, and the population is finite here, so that's 500. The mean age of the population is 72 years, right? And the standard deviation of the population is 5.3 years. right? If a sample of 50, so this is a sample of 50 people from this region is selected, find the probability that the mean life expectancy will be less. So find the probability that the mean life expectancy will be less than 70 years, right? So they didn't mention that this distribution is normal. However, the sample size is large enough, right? It's 50, so that's greater or equal than 30, right? That's greater or equal than 30. So we're good. We can use that assumption normality, right? So now let's calculate it, right? So notice also that this is finite population, so we're gonna have to use that correction factor. So this is C equals X bar minus mu X sigma, right? This is sigma X in reality, right? The standard deviation of the sampling distribution, but you need to use only sigma over n, right? So this is X. So X here, the mean life expectancy is less, so 70 minus, this is the mean of the sampling distribution, right? Mu X. So this is 72. Because they didn't mention that they're taking many sampling, they just mentioned in that. Remember that the mean of the sampling distribution approaches the mean of the population, right? So that's the reason I'm using that number. So sigma is 5.3, and then this is the square root of 50, right? And this is just calculation from here, right? So this is 92, and whatever that is, right? Oh, and don't forget, I was almost forgetting. I need to do the correction factor, right? That's the whole point of this video, right? So correction factor will be, I forgot to put it here. So from the formula is n minus n minus 1. Okay, so you do that. So this is n is 500 minus sample 50, 500 minus 1. And then you compute. So this is -2, and whatever you get, whatever number you get from there, right? So let's do that. 5.3 divided by square root of 50. And then we have square root of 450 divided by 499. And then you divide these two together. You get 0.7893. And then you divide those two together. And you get negative 2.53. So this is the same as probably the C-score is less than negative 2.53. You know that we don't, we have the C value to the left, that would be correct if this was positive, but however, this is negative, so we flipped, right? So this is C, greater or equal than 2.53. Remember, C value gives us the area to the left, not to the right, right? So this is 1 minus the probability of C less than 2.53. Let's look at the table. What is 2.53? 2.53. C value 2.53. 2.53. That's here, I guess. Yes. 0, 1, 2, 3. Yeah. 2.53 is 0.9943. 0.9943. So this is 0.9943. Subtract and we get answer, right? 1 minus 0.9943. And I get 0.057. Sorry. 0.57. Okay. So that's the answer for this problem. So notice that when the population is finite, I have to apply that correction factor, right? Okay. That's what the definition of correction factor states, right? Okay, so that was number 26. Number 27, let's do that. Just keep the answer, okay? This one, the green one, is the answer. Okay. A study of 800 owners in a certain area showed that the average value of homes was, so they give you the mean, 82,000, right? And the standard deviation was 5,000. What else? Find the probability that the mean of the home values is greater than 83,000, right? So the probability that the mean is greater than 83,000. So 83,500. So now I have the mean. So this is the mean of the sample distribution as well. And we have the sample, the population size is 800. The sample size was 50. And we can compute this, right? So this is PC greater than something, right? Do I have to apply the correction factor? Yes. Do I have to use normality? Can I assume normality? Yes, because the sample size is large enough. So C equals X minus mu over standard deviation of the sampling distribution. And you know that that's just sigma over N, right? So X is 83,500 minus 80,000. What's the mean here? 82,000. Yeah, 82,000. The standard deviation is 5,000. And this is N is 50, right? So let's compute. So this is 1,500 over whatever that is, right? So 500 divided by 50, we get 70.7107. 1,500 divided by that, right? Okay. This is 707. Okay, so when you divide that, you get 2.12, right? So this is 2.12. And now you need to find the C value, right? So you need to subtract 1 minus the probability of C less for the 2.12. Look at the table and you get your answer, right? 2.12. Okay, so 2.12, that's here. 2.12. So 2.12 is 0.9830. 0.9830. 1 minus 0.9830. And you subtract that and you get your answer, right? You get it's slightly different, but let me double check. Let's see. Oh, of course I get slightly different because I forgot to do the correction factor. That's the whole point of doing this, right? So N, I should put that here. Of course I'm gonna get slightly different. So N minus N, N minus 1. So I have to include the calculation here, right? So that's gonna be, what was the sample size? 800 minus 50, 800 minus 1, okay? So that's gonna be different. And this is gonna change, and this is also gonna change. So let's change that. Sorry about that. So 5,000 divided by 50, then square root of 579. Write those two together, you get 686. Okay, and then if you divide these together, you should get your answer. I got 2.18 this time. 2.18 actually, 2.18, and 2.18 in the table. 2.18. So that's the last one, right? So 2.18, where is 2.18? Yeah, this is 2.18, 0.9857, 0.9857, and I should get my answer properly now. 0.9857, and I got 0.0143. So don't forget to apply the correction factor when you have a finite population, like in this case, right? Don't forget to use this value, right? This is the correction factor, this thing right here. You need to include it in your answer. Otherwise, the problem might give you a slightly different answer, right? If they give you a finite population, right? And the distribution is normal, assumed to be normal based on the problem stating that, or based on the sample size is sufficiently large, then you can use this correction factor, right? So that's how you do those two problems with the correction factor. That's when you use it. So that's for these two problems, you have to use the correction factor, right? Because they give you a finite population. These two problems are different. I'm gonna do them. I'm gonna do these two problems, but these problems are not involved with correction factor or anything. It's just two problems that we have to use the central limit theorem or something like that, right? So let's do this. Let's practice, right? So here they're asking you the average breaking strength of certain brand of steel cable is 2,000 pounds. So that's the average, that's the mean. That's 2,000 pounds. And what is it? The standard deviation is 100 pounds. And a sample of 20 cables, so this is 20, is selected and tested. Find the sample mean that will cut off the upper 95% of all sample size of 20 taken from the population. Assume that the variable is normally distributed, right? They mentioned that because they give you a small sample size. Do you see that? They give you 20 only, right? Okay, so, and we can use since here the population is infinite, right? We don't know what is the population. We don't know, right? So we can use the normal formula, right? Or the central limit theorem formula, x bar minus mu x sigma, right? Right? The standard deviation of the sampling distribution, right? Or just sigma over n, right? But you have to read the question. Here they say find the sample mean. So they want this one. I'm sorry. They want this value, right? So you need to solve for that. So this is the same as saying sigma times the square root of n plus mu x. You have everything except you don't have the c value, right? And they give you the probability here. Is it the upper to 95%, right? So that should be 1.65. If you know your values, those special numbers, right? It's because they're asking you for the 95% in the upper tail, right? So you need to find that. So C should be greater than C. The probability of that should be 0.95, right? In the upper tail. So this is the same as saying 1 minus the probability of C less than C equals 0.95. Subtract 0.95 in both sides, so you get 0.05, and then you add this thing here. Anyway, we need to find a probability that the C value is 0.05, which is 1.65. I can just tell, right? So C, the corresponding C for that probability for the upper little part, the tail, right? Because if they're asking you for this, right? The upper tail. So this is 95%. Remember, two standard deviation is 95%. So they're asking you for this tail right here, right? This is the 0.05. So you need to look for that 0.05 tail, right? And I'm telling you right away, oh, it's negative actually, right? So if you look for that, so 0.05 in the probability table. So let's look for 0.05. 0.005, right? 0.005, that's here. So you can see, it's negative 1.6, and then you need to find this thing, right? Negative, and you add, right? Add, or combine like terms 0, 5. So this is going to be 1.65, but it's negative, right? You combining them, right? So it's negative 1.65. So this is negative 1.65, right? Sigma 100 square root of n 20 plus the sampling mean, which is 2000, right? And that will be your sample mean, right? So let's calculate that. This is multiplication, right? This is multiplying. Okay, so let's calculate that. And I got 1963.1. So that's the sample mean, right? Exactly the answer they had before. Okay, that's how you do that. Okay, let's continue. Okay, so that's 29 and 30, the last two problems. I think the last two problems are connected to each other when I did it before, I think I remember. Okay, so let me keep just the answer. Okay, the rest I don't need. So here they say the standard deviation of a variable, so you don't know what it is 15. If the sample of 100 individuals, right, is selected, compute the standard error. Okay, you know the standard error is this, right? This the standard deviation of the sampling distribution. So that's sigma over square root of n, right? So if you what they say compute, right? Okay, so that means that this is what 15 over root 100, right? 15 over root 100, that's 15 over 10, which is 1.5. Okay, and what is the sample size necessary to double the standard error? Okay, so to double the standard error, what is the sample size needed, right? So basically they asking you for this. You know the sampling distribution already. So this is 2 times 1.5, sigma is 15, and you need to solve for n, right? So you can just swap these two, right? So this is 3 anyway. So you let me do step by step. 2 times 1.5, you know that that's 3, right? So, and this is square root of n. Swap those two. So this is 3, square that, right? And equals 5 squared, which is 25. You're done, right? So what is the sample size necessary to double the standard error of the mean? 25. Okay, that's it. And I know that this is, I can assume that this is normal distributed because the sample size is large enough. They say a sample of 100 individuals, right? So that's larger than 30. That's good. Next question. I'm gonna keep the answer only. Okay, everything else can erase. So here they're asking you, in exercise 29, what size sample is needed to cut the standard error of the mean in half? So again, what was the standard deviation? Standard deviation was 15. And what else? Do I need anything else? Sample 100 individuals. Okay. Okay. What sample size needed to cut the standard error? So we have the standard error before, right? Standard error was 1.5, right? 1.5. So what size? Okay, so basically we need to cut it in half, right? So cut it in half means this, and sigma over n, right? So we have 1/2. We have this guy here. This is a sampling error, right? Sampling the standard error. So this is the same as 3/2. Sigma is 15. And again, I need to solve for that value, right? So this is 3/4, 15 root n, swap places, right? And goes here, 3/4 goes here, right? Multiply by 4, cancel. So this is 60 divided by 30, right? I'm sorry, 60 divided by 3, that's 20. And square that. For 100. So what sample size is needed to cut the standard error of the mean by half? 400. Okay, so that's it. I mean, that's the concept that I was explaining to you, the correction factor. If you still have questions, please send me an email. Thank you and have a nice day.